Example 4.5. Determine the current through the 2 ohm resistor at AB using a Thévenin equivalent circuit. This is an important conceptual example. Because there is a dependent source only method 2 can be applied. Always try to simplify the circuit using source transformations and reduction. In this case, there is no reduction available. So I can't do either of these. So then we move forward here. So now what we want to do here is that we want to go through our process. We want to go in and we want to determine VOC. So after we remove the load, here's our circuit. So what I'm going to see here is that I have a current source that's going up. Here's my open. Here's my 2 ohm. And then if I continue, so here's my 4 volt, here's my 8 volt. Now if I go to the upper loop, I see that I have a dependent source, 6i, and then I have a 2 ohm resistor, which looks like this. So this here is my VOC. There's my open. And because this is a dependent source, I have a current I going through here, so I can see that that gives me a polarity like that. So we always asked the same question. How would you solve for VOC? Are you going to use node? Are you going to use mesh? Are you going to use simple circuits? Whatever it is. And in this situation, I'm actually going to use simple circuits. And the reason why, so my choice here is I'm going to use simple circuits. And the reason why I think this is a good way of doing it is because look at the open. Because of the open, follow the 4 amp source. So if I follow the 4 amp source, look what happens to the current. The current from the source goes in which direction? It goes up like this, And here's my 4 amps. And you could see that I and the 4 amp source are in series. So we can immediately conclude that I is 4 amps, which then it tells me that I know what the voltage is of the 2 amp. Because now the voltage of the 2 amp has to be, of course, the resistance times the current, which is now 8 volts. And of course, we know what the voltage source is, the dependent voltage source, that's just going to be 24 volts. So now what I'm going to do here is that I'm going to apply KVL on the upper loop. And if I do that, it tells me this. Starting with my negative source here, with the dependent source, I get 6I1 plus the voltage of the 2 ohm minus the 8 minus VOC is equal to 0. Now, if I go in and I solve for VOC, you can see that the dependent source is going to be 6 times 4, so I'm going to get minus 24. We already know what the voltage of this guy, of the 2 ohm, and you can see here is that this is minus 24 volts for VOC. So now let's go to our next piece. Our next piece is that we want to go in and determine I short circuit. So if I go in and I look at the circuit, that means here I need to place the short at the open. And so what do I see here? So I see my source, which is a 4 amp. So if I now look at my short, look that I now have a short right here. Note that this is now a completely different circuit. And so let me put in my 2 sources. So here's my 8 volts, 4 volts, and then I have my dependent source, and then I have my resistor, and I'm right here. So here's my 2 ohm, here's my 6I, and then again, here's my current I right there. So I need to solve for I short circuit. So what's probably the easiest way to do this? So there's some shortcuts, but probably the most simplest way here, I'm going to label this as loop 1, which I'll call I. This guy here is the 4 amp source. And then this one, I have to give some arbitrary name, which I'll call IX. So if I look at this thing, note that I know everything about the current I because it only contains the variable I. So I'm going to have, just to be systematic about this, we have 3 loops, 1 current source. So I should have 2 loop equations. So I have the loop for the red I have the loop for IX, and then I'm going to need a solver for I short circuit. That gives me 3 equations, and I have 3 unknowns. One is IX, one is I short circuit. So if I look at my first equation, that's going to be the loop of I. So if I now apply a KVL loop here, right, I only have 1 resistor, so it should be 2I. And as I come around, look what happens. I have a dependent source and I have a constant source. So the dependent source stays on the same side. So that's got to be minus 6i. And then I take the 8-volt source to the other side, which then gives me 8. And you could see here is that this immediately gives me a value of I equals to 2a, 2 amps. So right away, I knew I always had two equations, but if we're going to be systematic about it, this is probably the way to go about it. Now, let's go look at our second equation, which is loop Ix. So you can see here that I have one resistor in the loop. So then it should be what? 2Ix, then I have a mutual of 2 times 4. And then my sources here, I get positive, so that's positive 12 on the left. If I take it to the other side, I get minus 12. So then that tells me here is that Ix now is going to be minus 2a. And then finally, I have my third equation, my solver for I short circuit, and you can see that it has to include loop I and the 4 amp source here. So the 4 amp goes with I short circuit, so it should be 4 minus I, and that has to equal I short circuit, but I know what I is, and so I is minus 2, so then this tells me here is that I short circuit is then going to be plus 6 amps. So now I could then calculate my Thévenin resistance. So my Thévenin resistance goes like this. So I take the ratio of these guys, and I'm going to get minus 24 volts plus 6 amps, and I get minus 4 ohms for the Thévenin resistance. This RTH value is correct and unusual. So if I now go back and I look at my original circuit, here's what we find. We find that our Thévenin equivalent is, here's my circuit, my original circuit, right? Here's my original circuit. And this is equivalent to a minus 24 volt source. I have my Thévenin resistance, which is minus 4 ohm. And then here is my load right here. And my load here is my 2 ohms. So if I want to calculate the current through this resistor here, I'm then going to apply Ohm's law. So if I apply this to Ohm's law here, so then I apply Ohm's law, and I get here that the current of the 2 ohm is then going to be RTH plus 2 ohms into VOC, but you're seeing here that I get minus 4 plus 2 minus 24, and I get positive 12 amps for I 2 ohm. So that is the current through that resistor. Now, what I did here is that I did PSpice to see if this answer is correct. So if I look at my PSpice results, right? So here's my my PSpice circuit, and result shows you that I have a current that flows like this. That's I2 ohm. And look at this, 12 amps. So that is really telling me that that's the current. So now what I'm going to do here is that I'm going to try to interpret this negative RTH value. Okay, I want to interpret that. So there's a couple of things that you want to really understand here is that a negative RTH value can only occur in circuits with dependent sources. Okay? It can only occur with circuits with dependent sources. This RTH value cannot be measured with an ohm meter. You can't put a meter and measure this negative resistance. Now, one of the things here is that what we find here is that negative RTH values make more sense in AC circuits. Okay, AC circuits where resonance slash impedance matching, it's spelled wrong, occur. So what I'm going to try to do here is that I'm going to try to see if I can make sense of it. And the way I'm going to do it is that I'm going to use an analogy of a resonant mass spring system. Now, the way I'm going to look at this thing here is that you have to imagine that you have a spring system with a cart. So what I imagine here is that I have a cart. And so when I'm looking at my cart here, I have two springs attached to this. So because this cart's at rest, we know that right here, this is our equilibrium point, which is equal to 0. So what I'm going to do here is that I'm going to displace this cart. That means I'm going to move this cart, let's say, to right here. So I'm going to displace this cart. So what this tells me here is that if the cart is displaced, and let go, it oscillates about the equilibrium. Right? It has simple harmonic motion. Its frequency, its natural frequency is omega naught. In other words, omega naught is related to the spring value, the mass times the square root, and this is what's called the natural frequency. Well, that's and a good way to interpret what we mean by natural frequency is essentially an object's own sound. So if you drop a fork on the floor versus a golf ball, you can immediately tell the difference between the keys hitting the ground versus a golf ball. And that's because they have their own natural frequency. Now, if now we drive / force the cart to oscillate at a driving frequency. So this driving frequency we'll call omega D. So how do we do this here? So I essentially take this system over here. So now I'm going to place my cart system here. So what I'll do here is that now I'm going to come over here and I'm going to add an oscillating arm. So this guy, what happens now is that it's going to oscillate in a circle. So in other words, this guy is moving in a circle, and this is an oscillating arm. So because of this oscillating arm, it forces the cart to oscillate back and forth. Now, here's what we want to do, though. What we want to do here is that we would like to derive the motion of this thing. Okay, so if one derives the motion and solves for the position, it is frequency dependent. But what I'm going to focus on, instead of looking at the full solution, I'm going to look at only the amplitude. So if I look at the amplitude, which does not include the signs and sine or cosines, this is the amplitude. This then reads omega d squared minus omega squared, plus you get a series of constants, and it divides into a constant. So the key thing here, when you look at this guy, this constant, this is due to damping. And since you can't get rid of damping, those terms always exist. So if I had a perfect system, then I would have no constants in the denominator. Now, if I go and I plot this thing, here's what we actually see here. So if I plot the amplitude as a function of omega d, by the way, I should have put d right there. And then this is omega d. What you're going to see here is that I get a peak in the amplitude that looks something like this. So right here at this point, you get omega naught. So if I look at that graph, we could see here is that when omega d equals omega naught, and this is what they call, I want to be careful, in AC circuits, this is what we call impedance matching / resonance. So when omega d is equal to omega naught, the amplitude is maximum. Because the denominator has a cancellation which makes it smallest. So no surprise. But now to get to our situation, here's the thing that which is where this gets really, really interesting. So if we had a perfect system, then the amplitude of omega d would be proportional to omega d squared minus omega naught squared. And so if I now resonated that circuit, in other words, omega d now matches omega naught, then this term here, the amplitude goes to infinity. Now, of course, this is not possible. So this is not possible, but it's more relevant to what we're doing right now. Now, let's go back to our circuit. So when we go back to our Thévenin circuit, we know that we have a voltage source that's negative 24 volts. We have our Thévenin resistance, which is minus 4 ohms, and then we have our load resistor. Now, what you're going to see here is that I'm going to assume a variable R load. So if I do that, you could see here is that if I go in and I calculate the current of this load. So if I calculate the current of this load, you could see here is that this is really going to be what? It's going to be minus 4 plus R load divided into minus 24. And of course, this is in units of amps. Now, what's really strange about the circuit here, one would think setting our load equal to 0 would get max current. This is an incorrect assumption. Now, again, I piece-spice this thing. Let me grab this guy right here. Oh. Let me grab this guy. And if I piece-spiced it, look what happens here. So what you're seeing here is that I can't set the load resistance to 0, so I set it to a very, very small value. And you could see here is that I load, when it's equal to 0, is then going to be -4 plus 0 minus 24. And this guy equals 6 amps. And if you remember from what we did earlier, when we did our circuit here and we did 2, look how it went to 12. So setting that R equal to 0 is not a correct assumption to think that the load current will be maximum if we set that. So if you want to get maximum current, to get maximum current, we need DC impedance matching. Slash resonate a DC circuit. But there's no oscillations in the DC circuit. So this is why you're seeing the quotes, because that doesn't make sense. It makes more sense in an AC circuit where you have oscillations. So then if I look at my max value, impedance matching implies that I need to make the denominator 0. I have to make it as small as possible. So then I'm going to take the limit where our load approaches 4. So if I do that, then I get -4 plus R load minus 24. And you could see this guy now approaches infinity. And it makes sense circuit-wise. So if I look at this thing, look what I have. This is equivalent to taking my 24-volt source. Here's my resistance. So you can see that this guy is 4 ohms. This guy's -4 ohms. So I am going to get maximum because now I essentially do what? I short out the power supply, right? I get I max when I short out the power supply. So now, look what happens. So if I come back with my piece by circuit, here's what I see. You can see here is that here's my current again. And look at the value. It's 2,400 amps. If I continue to do 0.99999, 3.99999, that current gets bigger and bigger and bigger and bigger. So what we're seeing here is that Thévenin resistance being negative is a correct assumption in the way you calculate this thing. So, however, real power supplies of course cannot put out an infinite amount of current. So in this situation, they max out at their maximum value. So whatever that is.